Hello everyone, today let's take a look at QB number 1 where we're going to derive the Poisson distribution. So basically you sit on the side of a quiet country road and after a very long time you notice that on average 3 cars pass you by per hour, and you also assume these 3 things here. And all of these things are very natural to assume, right? Number 1 is that cars arrive at a steady rate. So no matter what time of the day you are observing these cars, you see the same average number of cars pass by. So there's going to be no random spikes at different times of the day. Number 2, we have independent time intervals. So cars arriving in one time interval don't affect the probability of arrivals in any other time interval. And number 3 is pretty obvious, so we're saying that no simultaneous arrival. So if we make our time period small enough, so basically infinitely small, then we are assuming that only one car can pass by at a time. So you've been sitting at this road for a very long time, but now in the next hour we're going to observe cars, and we're going to let x be the number of cars that you observe in that hour. So it's asking us first, what is the probability that the number of cars that pass us by is equal to 4? And then in part B, we're just going to generalize what we find in part A, and that'll give us the PDF of the Poisson distribution. Okay, so in part A, we're given that an average of 3 cars passes by per hour. Okay, so the expected value of x, the number of cars that pass us by in a given hour, is going to be equal to 3. And somehow from this information, we're going to have to reverse engineer the probability that exactly 4 cars pass us by within the next hour, right? So what is this equal to? Well, we know the definition of expected value. In this case, x is discrete, so x can take values from 0 all the way up to infinity because it represents the number of cars passing by in a 1 hour period. So we could have 0 cars pass by, we could have 1, 2, all the way up to very large numbers. So the expected value of x is just going to be equal to the sum over all these possible values that it can take times the probability of that specific value occurring. Now the problem is that the question really doesn't give us much information about the underlying probability distribution. So if this is my time interval right here going from 0 to 1 hour, well, I don't know how many cars are going to come within this interval. First of all, it's continuous, so I have no idea what the probability is going to be because it could be anything from 0 all the way up to infinity. So to simplify this, just like with all things continuous, I can break it up into a bunch of little small subintervals, right? I'm going to say this subinterval right here is infinitesimally small, and I'm going to call it delta t. So I'm saying this time interval is really small, so small that in this time period at most 1 car can pass by at a time, which is exactly number 3. So even if 2 cars pass us by at practically the same time within 1 nanosecond, we're going to make this even smaller than that, right? It's going to be infinitely small. And what that allows us to do is be absolutely sure that within this time interval, either 1 car will pass us by or 0 cars will pass us by. And that means that this is an indicator variable. I'm going to call it I sub 1, and it's equal to 1 if a car passes us by within this interval, and it's equal to 0 if it doesn't. So here again, just like all the discrete distributions that we've done, here come the indicator variables that are going to make this problem a lot simpler. Okay, so our random variable x represents the number of cars coming within a 1 hour period. We can break up this 1 hour period into a bunch of really tiny little delta t intervals that are infinitesimally small. And then for this second subinterval here, I'm going to have I sub 2, which is going to have the same conditions that I sub 1 did. Okay, so now let's say I've broken up this 1 hour period into a ton of different subintervals. Each subinterval has this indicator variable that's equal to 1 if a car comes within this really tiny interval, and it's equal to 0 if it doesn't. So I have I3 all the way up to, let's say, I sub n. So now, just like we've done a million times, I can express x as a sum of all these little indicator variables. I'll say k going all the way from 1 all the way up to n because I have n indicators of I sub k. That's just again because x is the number of cars that we observe in 1 hour. So if we split that hour up into a bunch of disjoint little subintervals delta t, then we just sum up, did the car come in this interval? Did a car come in this interval? Did a car come in this interval? And when we do that, we're just going to get x. So now when I take the expected value of x, well, that's just going to be equal to the expected value of the sum of these indicators, which we also know by linearity of expectations just going to be equal to the sum of the expectation of the indicator, right? Okay, so now let's look at the expected value of one of our indicators. Let's just find the expected value of I sub 1. Just like with any indicator, this is just going to be equal to the probability that I sub 1 is equal to 1. So the probability that a car comes within that micro subinterval. Similarly, the expected value of I sub 2 is just going to be equal to the probability that I sub 2 is equal to 1. The expected value of I sub n is going to be equal to the probability that I sub n is equal to 1. Same is true for any indicator, so we can replace this term up here with the probability that I sub k is equal to 1. Now we also know that cars arrive at a steady rate. That was our first condition that we were given, so we know that the probability that a car arrives in this subinterval is going to be exactly the same as the probability that a car arrives in the exact same size next subinterval, right? So because we partitioned our hour into a bunch of really tiny equally sized subintervals, we know that the probability that I sub 1 is equal to 1. So the probability that a car comes in the first subinterval, well, that's just equal to the probability that a car comes in the second subinterval, which is equal to the probability that a car comes in any of the equally sized subintervals. So the probability that a car comes in any of these subintervals is going to be the same regardless of this iterator right here. So we're basically just iterating a constant. So this is just going to be equal to n times the probability that any of our indicators, so I'll just say I sub k, is equal to 1. Also, way back in the start in this specific question, 3 cars passes by per hour, so the expected value of x is equal to 3. So this value right here is just going to be equal to 3. Okay, now let me just move this down here to get some more room going, and like so. Okay, so n times the probability that an indicator equals 1 is equal to 3 in this case. So we know the probability that an indicator is equal to 1 is just going to be 3 divided by n. So assuming that the intervals are small enough such that only 1 car can come per hour, well, we know that the probability that a car comes in this interval right here is 3 on n, right? The probability a car comes right here, 3 on n. The probability a car comes in the next subinterval, 3 on n. So how do we know that no 2 cars can come within the same subinterval? Because we only have n indicators, well, we're basically going to end up sending n to infinity, and that's going to make these infinitesimally small, which will assure us that no 2 cars can come within that interval. But before that, now we actually want to calculate the probability that x is equal to 4. So now you can see where this is going. We're basically counting the number of successes among n Bernoulli trials. And from our second assumption up here, we assumed independent time intervals. So cars arriving in one time interval does not affect the probability of arrivals in any other. Okay, we have independent trials. That's everything we need for the binomial distribution right here. Why is that? One more time, I have all of these different subintervals, each of them having a car arrive within their period or not. So say I have a car arrive here, here, but maybe not the second one, and then this goes all the way up to n. I want the probability of exactly 4 cars arriving within this hour. All the trials are independent, so this one is successful with probability 3 on n. It's successful with probability 3 on n because they're independent. We can multiply them, and if it's successful with probability 3 on n, then it's unsuccessful with probability 1 minus 3 on n. And again, we've been over the binomial theorem. We have n trials here. We have 4 successes, so we basically have n choose 4 ways to arrange them. So the probability that x is equal to 4 is just going to be equal to n choose 4 times the probability of 4 successes occurring, and their independence. We can multiply them. So we take 3 on n to the power of 4, and then we have n minus 4 different failures, right? So we take 1 minus 3 on n to the power of n minus 4. Now again, in order for the whole binomial thing to make sense, we need a Bernoulli trial, so indicators with binary outputs, right? One if a car comes, or 0 if it doesn't. And we basically had to assume that n is going to infinity in order to make these subintervals small enough such that we are guaranteed that no 2 cars can come within the same subinterval. So now in order for the binomial theorem to work as a model, we basically just need to take the limit as n goes to infinity right here. Okay, so now let's just evaluate this equation down here. Actually, I'm running out of room. Okay, boom, new page. Now let's just evaluate this. We can first of all expand this binomial coefficient right here, n choose 4. It's just going to be n factorial on n minus 4 factorial times 4 factorial here. And then I just wrote out the rest of it. We can simplify it by just removing the constants. What are our constants? Well, this 4 factorial down here, and this 3 to the power of 4 up top. So I pull those out. I had 3 to the power of 4 on 4 factorial times this limit as n goes to infinity. Okay, now n factorial divided by n minus 4 factorial, we can simplify that. That's just n times n minus 1 times n minus 2 times n minus 3. Divide that by this n to the power of 4 that I have remaining, and then I'm going to just plug this back in. Now we can actually expand this term as well. Let's just write it as this times 1 minus 3 over n to the power of negative 4. So now if we just look at the limit as n goes to infinity of this term right here, well, if I send n to infinity, then the bottom's going to grow very small. This term's going to go to 0 basically, which is going to give me a 1 to the power of negative 4. So this whole term right here is just going to go to 1 as n goes to infinity. Okay, now we've simplified it quite a bit. Also notice that the limit as n goes to infinity of this term right here, well, this term here is going to be dominated on top by n to the power of 4, right? If I choose an n from all of these terms right here. So this term on top right here is going to look something like n to the power of 4, and then I'm going to have some coefficient in front of n cubed and some coefficient in front of n squared, and so on. But obviously when I take the limit, because I have an n to the 4 on the bottom, both the bottom and top are going to be dominated by their biggest term, which is going to be n to the power of 4, so these are pretty much irrelevant. And then when I take n to the power of 4 divided by n to the power of 4 as both go to infinity, well, this is just going to go to 1 as well. So now I've simplified down to this. Now I just need to find the limit as n goes to infinity of this term right here, and you'll notice this is a well-known limit, this is just going to be equal to, right here, is e to the power of -3. And maybe in the future I'll make a video proving this, but this is one of the most well-known limits. So now essentially we've solved this problem, right? The probability that x is equal to 4 is just going to be 3 to the power of 4 divided by 4 factorial times e to the power of -3. Now finally, when I plug this into a calculator, I get something along the lines of 0.168, so roughly a 16.8% chance, right? So in the end, given that cars come at an average rate of 3 and we hold these 3 assumptions to be true, well then the probability that in any given 1 hour period that 4 cars come is just going to be 16.8%. Basically, these 3 things were the exact things that we needed in order to model this situation as a binomial distribution. When we take the limit, it turns into a Poisson. So now in part B, derive a formula for the general case. Well, I'm not going to go do the whole thing over again because we basically already did it in part A, just with specific values of 4 and 3. But there's nothing special about these specific numbers. You could just do the exact same thing where you replace 4 with k and you replace 3 with lambda and you'll get the exact same answer. So now in part B, what's the probability that x is equal to k? Well, let's just plug in k where we had 4 up here, and let's plug in lambda where we had 3. So it's just going to be equal to lambda to the power of k times e to the power of negative lambda over k factorial. So I have a Poisson distribution with this PDF when these 3 things hold true, where I have this rate parameter lambda, which basically represents the average number of things that happen within a certain time period. And then to find the probability that a random Poisson variable is equal to some value k, well, I just plug it into this formula right here, and it'll tell me the probability of that exact number of events happening within that time period. So for instance, if we looked back in our case, well, what would the probability be that x is equal to 3? Well, we would expect it to be higher, right? Because we have an average of 3 cars passing by per hour. So I would expect that 3 is more likely. So let's plug everything into this equation right here. My lambda is 3. My k in this case is also 3. I have e to the power of -3, and then I divide that by 3 factorial. And when I plug that into a calculator, I get 0.224, or roughly 0.224. So that's going to be about 22.4%. So you can see that it is higher than over here, which is what we would expect. This is what the Poisson looks like when you plot it out. It's a discrete random variable. So we have this bar graph up here where the height represents the probability mass under it. In this case, I've set my rate parameter here to 3, mu equals 3, just like we had. That was when we were expecting 3 different cars to come every hour. And you can see that when we do that, the probability of a specific number of events occurring, the probability that x is equal to k, when k is 4, it's 0.168, which is what we got. And when it's 3, it's 0.224, which is also what we got. I'm sure I'll probably talk about this later, but you can see that when mu is small, so for instance, if I set mu equal to 1, my rate parameter 1, I expect 1 car to come every hour. It looks very left skewed, but once I make it larger, it's going to start looking more like a normal distribution, like you can see here when I set it to 100 cars an hour. And then one thing that we'll talk about later too to note is that the probability that x equals the average value, so in this case x equals 3, is going to be equal to the probability that x equals the value immediately before it, so x equals 2 in this case, right? If I set it to, let's say 5, I'm going to get the exact same behavior. Basically 5 here is going to have the same probability mass as 4. So yeah, that's pretty much everything on the Poisson distribution right there.